Okay, so this is section 11.5. We're on to video 2. We're continuing our examples with the alternating series test. So number 5 here, determine the convergence or divergence of the alternating series. Again, you can tell that from the -1 to the n plus 1, and then our ln of n over n. So let's try our criteria. Let's take the limit as n goes to infinity of the absolute value, which means get rid of the -1 term, of the natural log of n over n. And as n goes to infinity, the denominator grows faster than the numerator, so this one goes to 0. That is the first criteria. And then we'd have to show that this is decreasing. Since both the numerator and the denominator increase, we need to actually show it by creating a function. So f of x here would be the natural log of x over x. We're going to take the derivative to show the decreasing portion. So that's going to be, let's see, the derivative of the numerator is 1 over x times the denominator, which is x, minus the derivative of the denominator, which is 1, times the numerator, which is the ln of x, all over x squared. And we want that to be less than 0. So let's simplify. Numerator is going to give us 1 minus the natural log of x over x squared to be less than 0. X squared will not ever be negative, so we can basically eliminate that or multiply it on both sides, however you want to look at it. So we know that 1 minus the natural log of x has to be less than 0. 1 then has to be less than the natural log of x. Exponentiating, we know that e has to be less than x, or x has to be bigger than e. So as long as x is bigger than the approximate value of 2.71, we are good. And since n starts at 3 in our case of our sum up here, as long as n is greater than or equal to 3, perfectly fine. N is greater than or equal to 3. So this is going to work. The second part of the criteria is met. Therefore, this is a convergent series. All right. Example number 6. Once again, we have an alternating series. If we were to take our limit as n goes to infinity of the absolute value, it's the limit of n plus 1 over 3n plus 1. Well, that limit is 1/3. That is not 0, so that fails our first criteria. So then we can go back to the idea of the nth term test for divergence, which includes the -1 term. And since what's going to happen here is this is going to approach either infinity or 1/3 or -1/3, depending on if it's the positive or negative side. So it's going to bounce back and forth. We know that this limit does not exist, which means that our original sum is divergent. All right, one more example here. Let's see, convergence or divergence. Let's take the limit as n goes to infinity of the absolute value. Let's get rid of the -1 to the n. So we've got n plus 1 over n squared minus 2. That definitely approaches 0 since the denominator grows faster than the numerator. Criteria 1 is shown. And the second one, this one's not going to be as nice. Let's create our function. N plus, oops, not n, x plus 1 over x squared minus 2. Let's take the derivative of that to show where this thing starts to decrease, and hopefully it will always decrease after that point. So the derivative of the top is 1 times the bottom minus the derivative of the bottom, which is 2x times the top, all over the denominator squared. Again, that has to be less than 0. Again, keep in mind that our sum starts at n equals 3. So x equals 3 is the smallest value that we would start with anyway. And for every x value greater than 3, the denominator is always positive, so that really doesn't have any effect on anything. So let's get rid of the denominator and state that x squared minus 2, distributing the top, minus 2x squared minus 2x has to be less than 0. So it looks like x squared minus 4x minus 2 has to be less than 0. Okay, whoops, that is not correct. What I missed? Oh, yeah. That should have a squared on it. So it should, the line right above this, let's erase that one, should have been x squared minus 2 minus 2x squared minus 2. So what we get is, let's see here, negative x squared, combining terms, minus 2x minus 2 is less than 0. Or multiplying through by negative 1 on both sides. Remember, that's going to flip your inequality symbol. It says that x squared plus 2x plus 2 is greater than 0. And for every value of x that starts at 3 or bigger, since everything is being added there, that's always going to be the case. So this is going to hold true for all x greater than or equal to 3. Therefore, this series is convergent. What I will tell you is that while this is the case for some of these, most of the stuff that we deal with later on in the latter portion of this chapter, the alternating series test portion is relatively obvious as to whether it's increasing or decreasing if you're going to be using it. So these are slightly more involved, but the ones you use later when we get to the application portion are pretty easy to tell. All right, one last portion of this chapter is what's called the alternating series estimation theorem. And the reason it's called the estimation theorem is because there's no way for us to be able to utilize this test to get an actual value of the sum, but we can at least see how close of an approximation or bound our error is. So the alternating series estimation theorem says this, that the sum is going to be the sum of negative 1 to the n minus 1, why the n minus 1, I don't know, it could be n plus 1, it could be n, whatever, times b sub n is the sum of an alternating series that satisfies that b sub n plus 1 is less than or equal to b sub n. Okay, this is just stating that it's decreasing for the absolute values, and then the limit as n goes to infinity of b sub n is 0. Why we change this to b sub n from a sub n, I don't know. It's exactly the same thing. It's just basically saying you have to have, this has to satisfy the alternating series criteria first, okay, for it to be convergent and to have a sum. If that is the case, this absolute value of r sub n, that is our remainder, it's the absolute value of your remainder, is equivalent to the absolute value of the sum minus the sum of the first n terms, which is less than or equal to the b sub n plus 1 term. Okay, this is the key part right here. So our remainder, or the absolute value of the remainder, is less than or equal to, excuse me, let me start that over. The absolute value of the remainder is the same thing as the absolute value of s minus s sub n. Okay, we've seen this before. Okay, that's exactly the same idea that it was in the integral test. But the key here is because it's an alternating series, all of that is less than or equal to the b sub n plus 1 term. What does that b sub n plus 1 term mean? So let's take a look at this graphically real quick. So let's say we have an alternating series, and I'm not going to go a ton of terms out here, but maybe it's going to do this, and it is, ooh, that was bad, and it is fitting the criteria of an alternating series that is convergent because it's getting closer and closer to 0 as we go back and forth across the x-axis. Well, maybe I want to figure out what the remainder is for the first 5 terms. Well, if I look at just the first 5 terms, here's term 1, 2, 3, 4, 5. What this is telling us is that the b sub n plus 1 term, which is the next term in the series, this one right here, is the biggest possible error, or at least the biggest possible error has to be less than or equal to that value. Now, why does that make sense? If we cut this thing off right here and we start adding this term, this term, this term, no matter what, the absolute value of this one right here is the biggest possible thing you can have, because it doesn't matter where it is, whether it's on top or the bottom. If I take this, let's just say, for example, that this is -1/2. Well, that means maybe, I don't know, I'm making stuff up here, but maybe this one then becomes +1/4. One way or the other, you know its absolute value has to be less than the absolute value of the one before that, because it's alternating series and decreasing as it goes towards 0. And then maybe this one right here is -1/8 or something like that. If I start adding these terms together, every time I add another term, it's going to make it actually a smaller and smaller value, and it gets closer and closer to 0 by adding these alternating terms. And you can check that out if you want to. Take -1/2, add +1/4, you get -1/4. Well, that's smaller than -1/2 as far as its absolute value. Then if you add a -1/8 to that, it's going to keep decreasing in value. So the biggest possible error is the next term in the series. We'll actually write that out in words. So the size of the error is smaller than the b sub n plus 1 which is the absolute value of what's called the first neglected term. The next term in the series, the first neglected term. So if you wanted to find out what the greatest possible error was of the first 73 terms, the 74th term would be that biggest possible error, or the absolute value of that 74th term. So how are we actually going to apply this? Well, I'm going to be honest with you, sometimes it's a little bit of guess and check. So here we have the sum of this -1 to the n over n factorial. And it's definitely alternating. If you go through the criteria, which I'm not going to write down here, this passes the alternating series test for convergence. The limit goes to 0 for the absolute value, and all the terms are decreasing for the absolute value. So the thing it says here is it says find the sum. It doesn't say the sum exactly. It says correct to 3 decimal places. In other words, we want it accurate to 3 decimal places, so the third decimal place won't change. In general, we should know that when you round something, if it's 5 or higher, you round up. If it's less than 5, you keep it the same. So what we're looking for is something that is accurate to within 0.0005. So we want this to be less than that, because if the term that you have is 0.0005, the next thing would round up and it would affect the third decimal place. We don't want it to affect the third decimal place, so we're looking to find out what the term is that has, or the first term which is less than this amount. So how do we do that? Well, we have to take the sum of the first n terms. So we can do it term by term and try it that way. It's kind of a pain, but we can do it. 1 over 0 factorial. Then it's going to alternate minus 1 over 1 factorial plus 1 over 2 factorial and so on. Okay, and that's going to keep on going. And then what we could do is we can actually, well, we'll simplify some of these. So that's 1 minus 1 plus a half minus a sixth plus, let's see, 4 factorial will be 1 over 24. And that's going to keep on going. And we can figure out, okay, how long do I have to keep adding these things up before the third term, the third decimal place stops changing? And you can certainly do that. That's probably the longer way of doing that. Or you could just guess and say, what term is it that I'm going to plug into my calculator or whatever to see that gives me a value less than 0.0005. Well, since we've already done it, let's go ahead and take a look at what 1 over 24 is in the calculator. All right, so I pulled up the calculator here. If we just type in 1 divided by 24, well, it's 0.0416. So this term, oops, is 0.0146. I have to bring the calculator back. Okay, so that's not it. Obviously, that value is not less than 0.005. Let's just pick a term. You could pick, so that term right there is associated with what? 0, 1, 2, 3, 4. That's the fourth. Maybe try the sixth. Well, if we plug in, we're just guessing at this point. So negative 1 to the sixth divided by 6 factorial. Negative 1 to the 6 is positive. And 6 factorial, I know that 5 factorial is 120. 6 factorial then would be, I believe it's 720. Oops. So if we do 1 divided by 720, 0.0013. Again, that is not less than 0.0005. So 1 over 720. Oh shoot, I wish it would stop going away. Is 0.0013. Approximately 0.0013. Okay, so let's try the next one because I think we're getting close. So the next one would be negative 1 to the 7th over 7 factorial, which is, again, we take the absolute value. I should have done that here, even though I didn't need it. Let's do that here. So it's going to be 1 over 7 factorial. That one I actually don't remember. 720 times 7. $50.40. So 1 over 5,040, and that is 1 divided by 5,040. Ooh, 1.98 to the negative 4 power. So that's approximately 1.98 times 10 to the negative 4 power, which is the same thing as moving the decimal place 4 places to the left, which is going to be 0.000198. 198. That is less than 0.0002. So that right there is our first term. That's going to be the first neglected term, which says, since I've plugged in 7 there, that the sum accurate to the correct decimal place would actually be the sum of the first 6 terms. So I was actually pretty close here. We should have done minus 1 over 5 factorial, which is 1 over 120, and then plus 1 over 6 factorial, 1 over 720. So whatever these things right here add up to be, that is our sum, which I believe in this one I've already done in the past. If I plug all that stuff in the calculator, it gives us 0.368055. And that right there is a sum which is accurate to the to 3 decimals, because every term after that, as you can tell by this 7th term right here, is not going to affect this piece because of the fact that it's less than that 0.0005. It won't affect that piece at all. All right, that is enough for this video. We've got one more section of just series testing to go, and then we're going to start to apply it and see why we're doing all this in the first place.